MAT203 Module 3 Part 3 Lattices. Definition: lattice, a partially ordered set A less than or equal to, in which every pair of elements has a least upper bound and greatest lower bound, is called a lattice. Greatest lower bound corresponding to two elements x and y is denoted as GLB of xy, and least upper bound of two elements x and y is denoted as LUB of xy. Consider an example. The poset NR, where n denotes set of natural numbers with the partial order given by x related to y implies x less than or equal to y, is a lattice. So here LUB of xy is equal to maximum of x and y, and GLB of xy equal to minimum of x and y, where xy belongs to n. Now consider another example. Let S be any set and A denote power set of S. Then power set of S under set inclusion is a lattice. So to show that power set of S under set inclusion is a lattice, consider arbitrary elements B, C in power set of S. So least upper bound LUB of BC equal to B union C, and greatest lower bound of BC equal to B intersection C. So in the partial ordered set, if you consider two arbitrary sets of the form B and C, B union C and B intersection C exist for every two such arbitrary pairs of the form B and C. Hence, P of S under set inclusion is a lattice. In the Hesse diagram, this is null set. So if you consider two subsets, set A and set B, so set A union set B is set AB. Set A union set B, set AB. If you consider set B and set C, set B union set C is set BC. And if you consider set AC and set BC, its union is set ABC. If you take intersection, set AC intersection set BC, that is set C. So like that. So union of two elements and intersection of two elements in P of S exist, therefore it is a lattice. Now consider another example. The poset given by set of positive integers under relation R defined as A related to B implies A divides B is a lattice. Another example is the poset Z plus under division is a lattice. So same question. So to show that it is a lattice, consider any two arbitrary elements A and B, positive integers A and B, and here LUB of AB equal to LCM of AB, and GLB of AB equal to GCD of AB, which exist in Z plus. For example, A equal to 4 and B equal to 20, then LUB of AB equal to LCM of 420, and GLB of AB is GCD of 420. So both exist, therefore it is a lattice. Another example. So consider the Hesse diagram of a poset. Consider the elements 1 and 3. 1 and 3. So upper bounds of 1 are 1, 2 and 4, and also 5 is another upper bound. Upper bounds of 3 are 3, 2, 4, 5. So 2, 4, 5 are upper bounds for the pair 1 and 3. But there is no least upper bound, since 2 is not related to 4, 4 is not comparable with 2. 2 and 4 are both comparable with 5. There is no greatest lower bound, so this is not a lattice. So let n be a positive integer and dn denote the set of all positive divisors of n. Then dn is a lattice under the relation of divisibility. For n equal to 20, consider D20, which contains the elements 1, 2, 4, 5, 10 and 20, which are divisors of 20. So look at the Hesse diagram of D20. This is a lattice. Similarly, for n equal to 30, D30, this is a Hesse diagram of D30, which is also a lattice. Now here determine whether the posets represented by each of the following Hesse diagrams are lattices. So Hesse diagrams in A and C are lattices because in each poset every pair of elements has both a least upper bound and a greatest lower bound. But in the Hesse diagram B, the elements B and C have no least upper bound. Therefore, it is not a lattice. So here consider this B and C. So upper bound of B and C here D, E and F, but D and E are not comparable, so there does not exist any least upper bound. So least upper bound of B and C does not exist, hence it is not a lattice. Dual or reversed lattice. So if A less than or equal to is a lattice, then A greater than or equal to is known as dual or reversed lattice, which is obtained by interchanging GLB and LUB. Principle of duality. Any statement of lattices involving the operations star and plus and the relations less than or equal to and greater than or equal to remain true if star is replaced by plus and plus by star, less than or equal to by greater than or equal to, and greater than or equal to by less than or equal to. So to show that a poset is not a lattice, show that for at least one pair xy, GLB and LUB of xy does not exist. So consider set A equal to 1, 2, 3, 12. Here construct matrix tables for GLB and LUB of xy under the relation A division. So GLB of x and y under the relation division is given in this table. LUB of x and y under the relation division is given in this table. Any lattice satisfies certain properties. For any xy element of A, it satisfies idempotent law, commutative law, associative law, and absorption law. So if we consider idempotent law, x plus x is equal to x and x star x equal to x. Commutative law, x plus y equal to y plus x and x star y equal to y star x. Associative law, x plus y plus z equal to x plus y plus z and x star y star z equal to x star y star z. Absorption law, x plus x star y is x, x star x plus y equal to x. Sublattice. Let AR be a lattice. A non-empty subset B of A is called a sublattice if for any AB element of B, A join B and A meet B element of B. That is A plus B and A star B element of B. For example, let n be a positive integer and dn denote set of positive divisors of n. Then dn under division is a sublattice of lattice z plus under division. These are the few examples of poset. So here in the second diagram, for A and B there is no least upper bound, so it is not a lattice. So if you consider this Hasse diagram, for A and B there exists LUB and GLB, so it is a lattice. But when we consider this AB as a subset, A plus B, that is A join B, A star B or A meet B, LUB of AB and GLB of AB not in this subset, so it is not a sublattice. Fourth diagram, this is a sublattice. So when we consider GLB and LUB, it satisfies certain properties. X star y is less than or equal to x and x star y is less than or equal to y. M less than or equal to x and m less than or equal to y implies m less than or equal to x star y. X less than or equal to x plus y and y less than or equal to x plus y. X less than or equal to u and y less than or equal to u implies x plus y less than or equal to u. Some special lattices. Complete lattice. For a lattice we need to consider pairs of elements. So for every two elements subsets of a given poset, suppose there exists a least upper bound and greatest lower bound for every such two element subsets, then we say that it is a lattice. So if you consider a complete lattice, a lattice is called complete if each of its non-empty subsets has a least upper bound and greatest lower bound. So we need to consider all possible subsets. For a lattice we are considering only two element subsets, but here we need to consider all possible subsets. So for all possible cases, all possible non-empty subsets, suppose there exists a GLB and LUB, then we say that it is a complete lattice. So every finite lattice is complete. When we consider D20 under division, it is complete. So for an infinite lattice, Z plus under less than or equal to, consider infinite subset consisting of every positive, even positive integers. This has no least upper bound, so it is not a complete lattice. Bounds of the lattice. The least and the greatest elements of a lattice if they exist, are called bounds of the lattice and are denoted by a zero element and a unit element respectively. We can call this as 0 and 1. And a lattice is said to be bounded if it has a greatest element 1 and a least element 0. For example, lattice power set of A under less than or equal to under the set inclusion relation is bounded since it has 1 equal to A and 0 equal to null set. 1 equal to power set of A and 0 equal to null set. Another example, the lattice Z plus under division is not bounded since it has no 1. If you consider lattice Z less than or equal to, it is not bounded. It has neither 1 nor 0. So bounds of 0 and 1 of a lattice satisfies the following identities. For any A element of A, 0 less than or equal to A less than or equal to 1, A plus 0 is A star 0 is 0, A plus 1 is 1 and A star 1 equal to A. Complement of a element in a lattice. In a bounded lattice, an element B element of L is called a complement of an element A in L if A star B equal to 0 and A plus B equal to 1. Complemented lattice. A lattice is said to be a complemented lattice if every element of L has at least one complement. Example, consider the power set of A under set inclusion with 1 equal to a finite set, 0 equal to null set. The complement of any subset B of A is A minus B. So in this example, B star C equal to A and B plus C equal to 1. B star A equal to A and B plus A equal to B. Therefore, B does not have any complement. So, the given lattice is not a complemented lattice. Distributive lattice. A lattice A star plus is called distributive lattice if for any ABC element of A star B plus C equal to A star B plus A star C and A plus B star C equal to A plus B star A plus C. So in this example, power set of A under set inclusion, the greatest lower bound and least upper bounds are intersection and union operation respectively. So for any three arbitrary elements BCD of A, B intersection C union D equal to B intersection C union B intersection D. So intersection is distributive over union. Similarly, union is distributive over intersection. So show that set of positive integers under the relation less than or equal to is a distributive lattice. So here least upper bound of AB is maximum of AB and GLB of AB is minimum of AB. So first consider A star B plus C, that is minimum of A comma B plus C, and that is minimum of A comma B plus C is maximum of B and C. So this becomes maximum of minimum of AB, minimum of AC. So that is maximum of A star B comma A star C, which is A star B plus A star C. Similarly, A plus B star C, we can show that it is A plus B star A plus C. Therefore, the lattice Z plus under the relation less than or equal to is a distributive lattice. So in this example, lattices are non-distributive. So in the first Hasse diagram, we can show that A star B plus C equal to A star 1, that is A, but A star B plus A star C is B. So A not equal to B, therefore it is not distributive. Similarly for this second diagram,